Hall-Petresco theorem. And what it says is, if you take a product of alpha powers, you can express it using the so-called Hall-Petresco words, and the exponents are binomial, have binomial configurations. And because we're in a binomial ring, all these things lie in the ring, the exponents, that is. And this Hall-Petresco axiom allows you to prove that if G and H commute, for example, then GH to the alpha is G to the alpha, H to the alpha, right? So it's something that's needed for this technology to work. Yes.
So I guess it will also give you unique normal forms and.
Yes. So
they don't give you normal forms. The theorem of Paul says that each of the tau subi's lie in gamma subi, the lower central subgroup.
So tau I is in gamma I.
Well, what these things, where these show up, there's a theorem again that says you take products of these guys, let's say the G1 up to Gn form a Maltsev basis in your nilpotent group. Then when you multiply two such things or exponentiate, there are polynomials that allow you to do that, and the proof of that requires use of these tau subi's.
So an example of an nilpotent or power group is what? A module. I mean, if you take an abelian group, and so we're trying to generalize the idea of a module, basically, to the non-commutative case. And so a module is a nilpotent or power group, and also if you take a finitely generated torsion-free nilpotent group, and you can consider the R completion of that, and that gives you a nilpotent or power group as well. So there are many examples of these things. And, it's just an interesting idea. There's one more thing. There's a more general class called the class of exponential groups. And so the nilpotent or power groups are a subclass of that.
And 3 is definitely an axiom that's needed. You can't get away with just 1 and 2.
You
It doesn't follow. 3 doesn't follow.
3 doesn't follow from 1 and 2, right?
But it's possible.
I think it arises from when you try to do the rewriting process on the commutators.
Yeah.
And you have to strip, and you get the binomial forms and all this thing from the ring, as I recall.
Yeah.
Something like that. From the classical.
I mean, one of the big things is that tau sub 1, if you work that out, is the product of the G's.
Right. Just take alpha to be what?
Let alpha equal 1.
1. If alpha is 1, all of this disappears, right? Alpha is 1, so tau 1 is just G1 all the way to Gn. So you can work out the taus explicitly.
And also you can exponentiate a product using this axiom, which is something you couldn't do with just the other two.
Beautiful.
It's really cool stuff.
Yes, but anyway, so enough of that. Okay, so let's move on. So we're going to use this nice notation. NR denotes the category of nilpotent or power. So we are in a category. We're in a category of nilpotent or power groups, NR. And some more notation. It makes sense to talk about subgroups in this category and normal subgroups. So normal with relative to the action, and subgroups will have to be closed under the action as well. So subgroups in this category are like our submodules. H's are normal in G. Well, the conjugation has to happen relative to R. So we can find these things. This is a little technical. Essentially, we can also define in a natural way what it means for a subgroup, an R subgroup, to be R generated by a set. So rather than talking about generation, we talk about R generation. So it's the smallest nilpotent or power group which contains the set, right? So that's what that means. And that's a nice thing. This is a very nice thing. That doesn't happen in general for exponential groups. And so if you take an R normal subgroup of G, you can define the action of R on the quotient, on the coset space, let's say, in this way, and you get that G mod n becomes a nilpotent or power group. This doesn't happen in general for exponential groups. It does happen in the nilpotent or powered case. Okay, so well, the isomorphism theorems work in this category. Okay, so some definitions. Now this is something that we came up with here and there. So we discovered that we wanted a condition on R, and that condition on R was R had to be a UFD, because we were going to talk about primes, and it turned out that prime uniqueness and decomposition and all that stuff played a role. So we assumed R to be a UFD, and we define a ring element to be an omega member if all prime divisors are of alpha are in omega, or alpha is 1. So that's the definition of omega member. If you take G, which is an nilpotent or powered group, then you can talk about whether G has omega torsion. It will have omega torsion if G to the alpha is 1, where, again, this torsion is relative to omega members. And if every element is omega torsion, we say that G is an omega torsion group, and G is omega torsion free if the only omega torsion element is 1. So we have all these definitions. Why do we want R to be a UFD? Well, as we were doing this, we discovered that if we assume that R is a UFD, we don't get into trouble with reducible versus prime elements. So every reducible element is prime in a UFD. And also, you can multiply omega members, and you get an omega member. So that's kind of nice, and that's something we want. Right, Steve?
We were told this by a referee of our other paper that we wrote, where this notion came up for A groups, exponential A groups.
And he was worried about the fact that what happened with the reducible elements versus prime elements.
Yeah.
So we fixed it, assuming that R is a UFD.
That was it.
And if R is a UFD, that's...
Because, you know,
Go ahead.
you know, like this fact that the omega members forms a multiplicative set would not be the case if it wasn't a UFD.
That's right.
So, you know, you got to think back to your ring theory about that. I remember sitting in Starbucks thinking about it, spilling coffee on my chin
Yes.
as usual.
So that will be edited.
Yeah.
Send this video to Starbucks.
Because there's no, it has not been sponsored by Starbucks. Okay, so very, very well. Some more definitions. So these definitions are due to Steve. I didn't make them all. We made them all in his thesis, in your thesis or something. Well, so let's talk about finite omega type. A finitely R-generated omega torsion group is said to be a finite omega type, and then you're asking, where's the intuition? What does this mean? Well, what it means, take a single prime. If you take a single prime, this is like being a finite P group, for example. But in the case of nilpotent or power groups, we don't really care about things being finite. You're not going to get a finite number of elements. So that's why he defined this finite omega type. And R doesn't have to be a UFD, but since we're talking about a bunch of primes, then we might as well assume that R is a UFD. And the other definition, for this definition, R definitely doesn't have to be a UFD. So remember this Burnside theorem about groups in general. If you take a finitely generated torsion group, is it finite? In the category of nilpotent groups, the answer is yes. In general, the answer is no. Okay, now it turns out that that's the inspiration for this definition. So we say that a group is a finite type if it is nilpotent or powered, finitely R-generated and R-torsion. So we don't prove this theorem in this category, but rather assume these things to be a finite type.
Let me just mention that was my theory. That was my definition in the thesis. The omega one,
the other one
both of us came up with.
Okay.
So I give credit to you.
Okay, thank you. So let's talk about omega local groups. No,
Peggy,
she came up with.
Peggy hated the definition.
Yeah. So now you want to hear about omega local groups. So now you'll hear all about them. Take R to be a UFD, binomial UFD. So omega is just a set of primes, and omega prime is a set of primes, not in omega. So omega prime is a complement of omega. We're talking about primes in R. So R is any UFD you want. Okay, so Right, so what is an omega local group? Well, as I said before, in the classical sense, we want alpha roots to exist and be unique, where we have this notion of relatively prime. In this case, we take alpha to be an omega prime member, and if that map is a bijection, there's no algebra, there's no assumption of homomorphism, it's just a map, a bijection. If that happens to be a bijection, then roots exist and are unique. Alpha roots exist and are unique, right? So we term that an nilpotent power group, which is omega local. So here's a nice remark. It's what I said, so I won't say it again. So now, take H to be an R subgroup, and I'm just going to tell you what it means to be omega prime isolated. We use isolators as well in this work. So yes.
Omega prime doesn't have to be finite in any case.
In this discussion, no. But when we get to the residual stuff, we had to assume that omega was finite. Otherwise, it didn't work.
But omega prime doesn't have to be.
Omega prime will not be finite. Exactly. Well, I mean, none of these things have to be finite at this point. Yeah. So an omega could be everything, all the primes in the ring. An omega prime would be empty, and so on. So. Okay, so H is omega prime isolated. If G or the alpha in H means that G is in H for all omega prime members in alpha. So now the question is, let's ask, if you take an omega local group, when is a subgroup of omega local? Well, it has to do with isolators, it turns out. And so take H to be an R subgroup of G. H itself will be omega local if it is omega prime isolated. And what's interesting about this is to study these omega local subgroups of an omega local group. And so we have a lemma about that. And the lemma is exactly about when a subgroup is omega local. So this is something that is true in the classical theory, and we were able to get it also. So if G is omega local, then take N to be a normal R subgroup. N will be omega local if and only if the quotient is omega local. So it's kind of a nice thing you want to have. And a slightly more involved thing, but it's not too hard either, is that if both N and G mod N are omega local, then G itself is omega local. So sometimes it's easier to look at N and G mod N. So you can think in terms of 1 N G mod N 1. So if you look at these two are omega local, then this two is omega local as well. Okay, so very nice. That's a long story. I won't ask you to read all of that. Essentially, this is the definition of what it means for a set to generate a group as an omega local group. And it's basically the smallest, if you take S to be a set, then the smallest omega local subgroup containing that set, that's the omega local group generated by that set. So I don't know if that makes sense, but that's what it's there.
This is the mass of spirit.
It's the mass of spirit.
The mass of spirit. That's okay, so then we have a lemma. Suppose G is omega local and R is a of D. And furthermore, suppose that H R generates G omega locally. So every notion is relative to being omega. Hence the title of the talk, localization. We're talking about local things. Then G and H have the same nilpotency class. So that can be established. Now this is a very easy thing, actually. It's not terribly difficult, so it's an easy lemma, but it turned out to be useful for us. If you take two homomorphisms, ordinary homomorphisms, and you check that they are the same on the generators, then that's enough to say, well, they are the same. What about on the omega generators? Well, this lemma essentially says same thing happens. So if you take two homomorphisms of omega local groups, they are equal on the omega generators, they will be equal everywhere. So you can extend that stuff. Okay, this lemma is the analog of saying a P group is P local.